I'm Thomas Gomes, and this is MyComat. MyComat explores how we can use fungal materials, and specifically mycelium, to create a new generation of insulation materials. The idea is simple. Instead of relying only on conventional synthetic products, can we design materials that perform well acoustically and thermally, while also offering a more sustainable end of life? That is the challenge we are trying to address. So when we think about insulation, we normally think about what happens while a building is being used, keeping heat inside, controlling noise, and improving comfort, but insulation can remain inside a building for decades. And when that building is renovated or demolished, the material has to go somewhere. MyComat starts from that longer perspective. Not only how an insulation material performs during its useful life, but also how it is produced and what happens to it afterwards. Today, the insulation market is still largely dominated by non-renewable materials. Foam plastics, glass wool, and mineral wool account for most conventional acoustic and thermal insulation applications. Natural and alternative materials still occupy a relatively small part of this landscape. So the opportunity is not simply to create another insulation material. The opportunity is to develop an alternative that can compete in performance while addressing sustainability, end-of-life limitations from the beginning. It becomes particularly important because insulation is not a short-lived product. Buildings may go 20, 30, or even 50 years between major renovations. At the end of that period, conventional insulation can become part of a complicated construction waste stream. Many of these materials do not readily degrade, their disposal routes are not always straightforward, and their production can also carry significant embodied carbon. So there is a gap between the long service life we need from insulation and the environmental consequences we face when that service life ends. This is where fungal materials become interesting. Mycelium allows us to transform biological growth into a manufacturing process. By controlling how the fungus grows, what substrate it interacts with, and the geometry of the final structure, we can obtain very different forms of mycomaterials. They can be porous, they can grow around existing structures, or they can be incorporated into specially designed geometries. And because the system is biologically based, it also opens the possibility of alternative end-of-life pathways compared with conventional synthetic insulation. The key player is the mycelium. Mycelium is the filamentous network produced by fungi. So you can think of it as an extremely fine interconnected structure that grows through and around organic matter. As it grows, it binds material together while simultaneously breaking down part of that organic matter to obtain nutrients. That gives us several ways of working with it. Instead of having only one manufacturing process, we can change the substrate, the inoculation method, the growth conditions, and the geometry we want the mycelium to interact with. This is also where MyComat differs from many conventional mycelium materials. The common approach is to grow mycelium through loose biological substrates and use the mycelium essentially as a natural binder. We want to go further than that. We are investigating mycelium as a functional treatment for engineered scaffold structures, and we are also incorporating it into resonant acoustic systems. In other words, rather than asking mycelium to provide the entire structure, we combine biological growth with geometries that are deliberately designed for acoustic performance. And this is where the concept becomes measurable. On the left, we see how applying the mycelium treatment to a scaffold can substantially increase its sound absorption compared with the untreated structure. On the right, we see a second approach using Helmholtz-type resonators. Changing the geometry and introducing mycelium around the resonator neck modifies the frequency range over which the system absorbs sound. These are two different mechanisms, but they illustrate the same idea. We are not treating mycelium only as a sustainable replacement material. We are using biological growth as an additional design parameter for controlling acoustic behavior. The broader market opportunity is significant. In this deck, we estimate the relevant market at approximately 13 billion euros. At the same time, European initiatives continue to encourage improved building insulation as part of efforts to reduce energy consumption, while demand for products with stronger environmental credentials is increasing. But there is still a challenge. Natural insulation materials have grown relatively slowly compared with conventional solutions, and our own process is still at laboratory scale. So this is both the opportunity and the barrier. The demand exists, but we still need to demonstrate that the technology can become reliable, repeatable, and ultimately scalable. Today, MyComat is still at the laboratory stage. We have successfully grown the materials, demonstrated the use of biowelding in resonator systems, and observed promising improvements in sound absorption. The next step is validation. Over approximately the next 6 months, the priority is to establish the physical repeatability of the acoustic results. Between 6 and 18 months, the goal is to characterize thermal insulation performance and optimize the mixtures used for liquid mycelium treatment. And from roughly 18 to 24 months, the objective is to move toward larger scale material designs. So we already have evidence that the concept works. The challenge now is to transform that laboratory result into a repeatable material system that can eventually operate at a much larger scale. Thank you for listening. If you find this project interesting and see potential in what we are building, I invite you to join us and help take MyComat from the laboratory to the next stage